Yeah, friends, very good morning. Previous class, it was the study of a dipole. First, we have began with understanding the terminology with respect to dipole. Then, we have calculated the most important part, intensity at an axial point or equatorial point. Later, we have continued our topic, like dipole placed in an external uniform electric field. Is it not? You can call it either placed or you can also call suspended. There we have found a point that the dipole experiences a torque given by the expression tau bar, a pseudo vector, is P bar, the dipole moment vector, cross E bar, the field vector. And most important point, already I have told you, and one more time I repeat that, the sole purpose of this torque experienced by the dipole is to align the dipole in the direction of field. Why the tendency? You might have got one curious doubt as well. Yes, we will have an answer for that as well. So that torque always aligns the dipole, tends to align the dipole in the direction of the field, and we have seen those cases of zero torque. In the case of zero torque, we have two cases, like stable equilibrium position for theta equal to 0 degree and unstable equilibrium position for theta is equal to 180 degrees. Remember, last class we have shown those orientations also. One more time, go through the video, pause there, look at the orientation, or else you go through your notes which you have practiced. Now, we'll continue with the same concept of dipole placed in external electric field. See, before I start our new topic, new principle, for most of the students, you might have got a kind of rational doubt. What is this dipole? Why this dipole? Why we are studying this concept of dipole? Because it is a system of two equal and opposite charges, finite separation, like this. In fact, you remember, this is the concept which is very much basis for most of the concepts in chemistry. Dipoles, when I said, there are many such naturally occurring dipoles. And I refresh your knowledge of chemistry, high school chemistry, and as well your PU first year. You have these molecules through the chemical bonding, maybe the ionic, covalents and so on, right? And in the case of ionic, you know that in the case of ionic sodium chloride, Na plus Cl minus. So whatever charge bears the sodium ion, the positive, the same but negative charge bear by the chloride ion. So there are nothing but two charges, and that bond length becomes now the dipole length. All such cases, even in fact not only the ionic compounds, even in the case of covalent compounds. Covalent compounds you have come across, polar covalent and non-polar covalent, you remember? We take up the topic in the latter course also. Just to remind you that what is meant by that polar covalent bond, maybe in the loose terms, chemistry teacher might have told you that unequal sharing of the electron pair. In the case of HCl, it is not the case of exchange of electrons, one losing and one gaining. No, it is actually sharing of the electron pair. In that, more electronegativity, less electronegativity, that concept of chemistry. Because of that, there is a partial positive charge on the hydrogen and a partial negative charge on the chlorine. This gives rise to a concept of, again, dipole. So most of these covalent bonds may be like polar covalent bonds and ionic bonds, wherever you come across, all those molecules one will see them as the dipoles. Now, when such substances placed in external magnetic field, what will be the behavior? Is it not? And that is what is the basis or fundamentals that here we are discussing now. So all all such dipoles in an external uniform field, right? We said no translational because the net force is 0, but there is a couple that gives rise to torque and rotational effect, the torque tending to align the dipole in the direction of the field. Now, one more concept of this dipole and placed in electric field, the concept of energy. The work and energy is another aspect. Remember, I have told you, any of the discussions in physics, it consists of either motion or energy or work. If not, it will have the concept of wave. Now here let us see the energy concept in this following discussion. Now earlier we said it is placed at an angle and the torque will align. But now to begin with, I have placed a dipole in external uniform electric field, and it will be in the equilibrium position. Theta is equal to 0 degree P bar parallel to E bar. Now supposing if I want to rotate the dipole, if I want to, yes, a small rotation of the dipole about its center, supposing I have did. Rotation of the dipole about its center. What happens? Right? Now this is very much similar. Remember, in the first we also have done many such things like supposing an object, a body on the ground is lifted to certain height. What was the case? Lifting is always against gravity. Gravity always acting downwards. Supposing if it is lifting, it is against gravity, and anything against force requires work to be done. And in the case of rotatory motion, anything against torque, we say. In the case of translatory motion, we say anything against force, work needs to be done. Whereas in rotatory motion, anything against torque, work needs to be done. See, these are what are our fundamentals. These fundamentals we will use from smaller things up to our JEE mains, advanced NEET or whatever it is. So this is how you read the question. Now here, there is torque experienced by the dipole which always tries to keep it in the direction of the field. Therefore, for the rotation, it is against torque. That work against torque, if it is the case of, we have said in the very beginning, you remember, this Coulombic force is a conservative force, and hence electric field is a conservative field. And what is the nature of the conservative field or characteristic of the conservative field? Work against force or work against torque stores as potential energy. So what is our title for the talk now? The potential energy of dipole. The concept is potential energy of the dipole placed in external uniform electric field is our question. Now this is what is a small representation that we have shown again. Physics. This will tell you now everything. Let us consider a dipole of dipole moment P bar placed in external uniform electric field of intensity E bar, such that the dipole will be now in equilibrium position after. Even if we place at an angle, because of the torque, it will come. Now, if the dipole is to be rotated, work is done against torque, and that work done will now calculate. Now see here, initially it is in theta equal to 0 degree position, right? Now the concept in physics, one more time you will see. Wherever it comes the case of work against force or work against torque, look at this concept. Now supposing I am showing this new position, this is what is rotation of the dipole about its center. Rotation about its center by an angle theta. Then now as theta changes, actually torque also changes. Therefore it is not a constant torque. If it is a constant torque, we can use a straight formula. What is that? Work done is equal to torque into angular displacement. But here torque is a variable. Therefore we cannot use tau is equal to, or W is equal to tau theta, we cannot use directly. Therefore this is what is a simple calculus method that we do. Right? It goes like this. Again, the same concept which you have used in your first PU. Let dipole be placed, dipole be turned by angle d theta, a small angle I am taking. By an angle d theta against torque. Right? Therefore, now we say torque tau is equal to, this is what is PE sin theta, if theta is the initial position from where we have turned by d theta. Therefore, let us say that the dipole be turned by an angle d theta against torque from a position theta degree, right? So theta degree was the initial position. It could be anything. It not be 0 or it can be any of the numbers from 0 to 180. So from theta degrees it is turned by an angle d theta. Now tau is equal to P sin theta, work done against torque. Work done against torque. We will now write it as dW. It is a small work done for this small rotation. dW is tau times d theta. Tau times d theta. Therefore, now we are calculating total work done. Yes, to turn dipole by an angle, suppose alpha. That is, initially it was in theta degree position. Now it went to another position so that the angle of rotation is alpha, turned by alpha. Then this total work done is nothing but integral dW. I will write this as from theta 1 position to theta 2 position. Afterwards we will do that. So W is equal to integral dW, a small integral. Now we will evaluate. Remember, this will be your fundamental. This is not a derivation, no confusion. Every time I tell you what is the first line of any principle, that will become the very simple following steps for a derivation. Now we said dipole turn, torque dW is equal to tau d theta. This is integral dW. Therefore, now our principle was work against torque stores as potential energy. Therefore, this potential energy U is equal to. In the notes or in the examination, you will mention that statement. What is that? This, okay, let me write that. This work done against torque stores as electrostatic potential energy. Here now I call it potential energy. Remember, potential energy, whenever it comes, it has always an adjective. The one which we have discussed in our first PU, you remember? Potential energy, MGH you have taken, that is gravitational potential energy. Remember also you have got in the case of elasticity also, potential energy you have calculated, and we there call it as a strain energy. Even in the case of surface tension also you have calculated potential energy, and that is called as surface energy. So wherever we come across potential energy, it will be of different forms in the different cases of conservative forces. Now here, this work done stores as, I simply call it potential energy, means electrostatic potential energy. So potential energy, now we, in the next line we got our expression. Now let me evaluate this integral. What is that? You will see. So this U is integral, earlier we said that dW is equal to P E sin theta times d theta, right? We know that this P is a constant term out of the operator, so this is simply P, yes, integral sin theta d theta. a simple integral. Integral sin theta d theta is minus of cos theta. Therefore, our final expression will give u is equal to minus of p e cos theta. P cos theta. Now give a pause for the video at this stage. One more time, you look at these two simple steps and understand each and every term. Give a pause for the video whenever there is a good figure or what you call as a derivation, or if I speak something as LHS, RHS and how to find the relations and the other aspects. Give a pause for the video and have good observation. Now, this u is equal to minus of p cos theta. This is what is potential energy. Look at this. This is in the form a b cos theta. Once again, our knowledge or understanding of vectors. We said a b cos theta is the dot product of a bar and b bar. Here also, dipole moment a vector, field is a vector. Therefore, now this is p e cos theta term means that u, the potential energy u is equal to negative of p bar dot e bar. No brackets, let me write. Negative of p bar dot e bar. This negative sign is very significant. Without negative sign, don't use this potential energy. I repeat, potential energy of dipole, whenever we are using, along with this negative sign, we have to use it. Now here comes. After this, of course, you have your simple derivation and you have a very popular principle, potential energy. What are the keywords? Dipole, electric field, yes, potential energy, the keywords. In such case, this u is equal to minus of p bar dot e bar. Now you see, I will write what is that u maximum, what is the maximum potential energy. Yes, this is minus of p dot e or reverse minus of p cos theta. For cos theta is equal to minus 1, this becomes u is equal to plus p, because cos theta is minus 1, cos 180 is minus 1. Then what is u maximum? U maximum is plus p times capital E. Remember, I am writing small p for dipole moment, E for the field. U maximum is plus PE. That is for theta is equal to 180 degree position. What is the theta equal to 180 degree position? We have learned the terminology of, yes, unstable equilibrium. So U maximum is plus P for unstable equilibrium. Unstable equilibrium, yes, brackets theta is equal to 180 degrees. And now you repeat, what is the U minimum? U minimum. And this is a bit interesting as well, because many a times when we are doing that minimum, many a times that minimum value happens to be 0. But here you see, we have this negative sign, and that is what I said more significant. Along with the negative sign only it has to be used. In such case, suppose if I say cos theta is equal to plus 1, cos theta is equal to plus 1, it becomes minus of PE. And that is what is the minimum, not 0. Because in the numbers you know that positive numbers 0 and the negative numbers when you take minus 2 and minus 5, you say minus 2 is greater than minus 5. Is it not? Now 0 and minus 2, you say 0 is more. And therefore, in this case, the minimum potential energy is never 0. Underline this point, you make it underline and you please tell yourself once or twice. U minimum is equal to minus of P for the case of theta is equal to 0 degrees, which of course we have got it as for stable equilibrium position. Stable equilibrium position. Now, one more of course, U can also be 0. When is U 0? For theta is equal to 90, cos theta becomes 0. Therefore, potential energy is 0 when dipole is placed at right angles, that is perpendicular to magnetic field. Torque is maximum potential energy is 0, because earlier we said tau is equal to PE sin theta. For theta is equal to 90, yes, torque is maximum, but potential energy is 0. Zero potential energy for dipole is not a minimum value, remember. Here is one such example. Next time also, in the case of potential energy or other cases also, we may find this kind of situation where 0 is not a minimum, but something negative value can be its minimum value. Now, during this discussion, you have found one expression for potential energy under maximum and minimum conditions. Now you see, earlier we have given one statement that the purpose of the torque on the dipole is to align the dipole in the direction of field. Now let us put a question, why so? Why the dipole experiences the torque and always it tends to align in the direction of the field? Here is the answer. Now in the direction of the field means theta is equal to 0 degrees. Theta is equal to 0 degrees, you see here, potential energy is minimum. Potential energy is minimum. And what is a kind of principle in the nature? Always lesser and lesser energy, more and more stability. The higher energies are always unstable, and therefore the tendency of any entity in the nature is to acquire stability with by possessing as minimum energy as possible. Therefore now here you will see that for this theta is equal to 0 degree position, the potential energy is minimum and hence more stable, and that is why the torque always tends to align the dipole in the direction of the field. So after the concept of torque, we have this concept of potential energy. Now the same expression, if I use it, if I extend it by one more line, we get an expression for work done to rotate, right? So let us see that expression for work as well. Mr. Bandapi?
Sir,
Time note is
22. 22.
22 minutes banta. 22. So when we are writing the expression for work done, again it is a simple work energy principle. Remember, all these fundamentals are dealt in our first period. Work and energy are like two facets of a coin. Energy related with work and work always due to energy. This is how we have done, and that is called the work energy theorem. Nothing but another form of conservation of energy. So work energy theorem can be two ways. Right? What is that? Work kinetic energy theorem or work kinetic and potential energy theorem. Now here we are talking about work energy theorem means work and potential energy. Because when we are rotating a dipole in external electric field, as its orientation theta changes, yes, potential energy changes, and that potential energy, the change is what is work done. Therefore, if now I am writing here the given situation, if dipole turned from theta 1 degree position to theta 2 degree position. So this is the situation. Please remember, don't rely on somebody to give you some PDF forms or some Xerox copies for your notes. That will be the worst case even at this stage of 12th class. You have a very, very beautiful representation, understanding that, and a simple English. You can write your own notes and it will be the best one, I am telling you. And you should have this practice at least in 12th class. because I have found some of the students giving kind of request for notes or the material for the syllabus that is happening. For God's sake, please try to avoid that and write the notes of your own. Now here, theta 1 to theta degree position, therefore now I am writing this is what is it. Tau 1 is minus PE cos theta 1 at theta 1 degrees. I am telling you, don't forget this negative sign, right? So again, what is the, I'm sorry, not tau, this is U, right? So this is what is U1, that is what I call initial. Ui is equal to minus P cos theta 1, and at theta 2, this is what is Uf, this is minus of Pe cos theta 2 at theta 2 degree position. Therefore now you will write using work energy theorem. Using work energy theorem, yes, W is equal to delta U, the change of potential energy. So the change in potential energy. Whenever you write it for a change, sometimes that final value, that change, higher minus lower sometimes, most of the times. But remember, wherever you come across this kind of negative sign, there writing that difference needs to be in perfect order. The change is final value minus initial value, because with this negative sign, final minus initial and initial minus final, you will never get the same number. Maybe number same, but again the concept of negative positive sign comes. So that is why as a mandatory or as a default, let us always change, write it as final minus initial. Therefore now this delta U means final energy minus initial energy. So that now you will take all those common, minus P, you will take it as common, right? So W is equal to, if you take that minus P common, it will be cos theta 1 degrees minus cos theta 2 degrees. So this is what is the expression for the work done. Now of course you will find here this negative sign, which is quite obvious that if we are rotating, turning against torque, you will get work as negative. Instead, that is what we call work done on the dipole. We have also other cases like work done by the system, right? Work done on the system, where that theta is what is the matter. Work done by the gravity, work done against gravity. Such things we have discussed with beautiful and interesting examples as well. So here, this negative sign is having a significance. Supposing finally you get W as negative, what does it mean? It is against torque. Supposing I have rotated from 0 degrees to 30 degrees, yes, it is negative. From 30 degrees to 60 degrees, yes, it is negative. And supposing if the dipole is simply placed at an angle 60, and if suppose it comes to 0 degrees, then the work done is positive. So work along with that number, the sign has a great significance, right? So this minus PE times cos theta 1 minus cos theta 2 is our expression. Remember, all these principles will form the basis for good models of our different examples, starting from board examination to any other examination. So this is what is the case of work done, rotation of the dipole. Now here, as a small extension of this topic, one more case we will study. What is that? Just you practice this one as work changing potential energy. As a next topic we will do one very interesting thing. Again the fundamental for the upcoming topic is also nothing new. And again that fundamental which we have learned in our first week. Let us see that. Now let us consider a dipole of dipole moment p bar placed in equilibrium position in external uniform magnetic field of intensity E bar. So this is the situation. Now from the equilibrium position, if I simply displace it about its center, of course, about its center by adding theta and then release it is, see, look at this example, it is, this dipole is turned by an angle theta and released. What happens? For this theta degree position, earlier it was in equilibrium, torque is 0, but now it is turned by an angle theta, yes, it starts experiencing torque. So when we release at this position because of the torque, what happens? Yes, the tendency to align in the direction of it. Therefore, gradually from theta degrees to it will come to 0 degrees. But now here it comes. As soon as it comes to theta equal to 0 degree position, no doubt torque becomes 0. Torque becomes 0, but it does not stop at once, and this is what is the property of inertia that we have studied in our first PU. Remember? Supposing fan is running, the fan is running due to power supply. Suppose the moment you switch off the power supply, do you find the fan coming to rest at once? No. It comes to rest after making few more rotations. That is what is the property of inertia. Here also comes the same question of inertia. But this time it is not linear inertia, remember. Why? Because we are talking not about translatory motion, it is all rotatory motion. From this position, it comes to this equilibrium position, torque becomes 0, but due to inertia, now it will come the other way. Earlier we have rotated, but now this time it comes to this position because of inertia. And now, as it start moving the other direction, again torque experiences, therefore at this position it stops and again it comes back. Now finally, what is that we observe? A dipole, supposing if it is suspended or placed in external uniform electric field, if it is slightly displaced and released, what will be the case? That here I show. Supposing the field is towards your left hand side and this is the dipole in the equilibrium position. Now if I just slightly displace it from the equilibrium position, then it again comes to equilibrium position the other way and so on. The same will continue. As a result, what you find is that this dipole will make now oscillations. Oscillations not like this, you see. This is how it is, suspension is visualized. This will come this way and then this way, that way. So it makes now oscillations which are called as angular oscillations, right? Therefore, a dipole placed in the external uniform electric field, when displaced from its equilibrium position, it makes angular SHM. It makes angular oscillations. And what are the reasons for the angular oscillations? Yes, the torque and inertia, which we call it as moment of inertia, the rotational inertia in this case. This can also be a kind of conceptual question. So what is the basis for the angular SHM of this dipole? Yes, torque experienced by the dipole due to the external field and the inertial aspect of this dipole. Because these two, when we understand as a basis, making a simple derivation is very, very easy. Now, what is that angle and what is that angular SHM and what are the characteristics is now our study. Now let us see. Torque on dipole. Torque on dipole, we will write it as tau is equal to, yes, PE times psi take one simple mathematical approximation that when theta is very small, sin theta can be taken as theta. Also tan theta can be taken as theta. That approximation now I am using here. Therefore now I am writing for small rotations. For small rotations from equilibrium, this sin theta now I will write as theta. Therefore my expression is torque is equal to P E times theta. And remember here also I will take this torque with the negative sign. Why I will take this torque with negative sign? Because it is showing the restoring nature. Supposing if I am rotating like this clockwise, then it is making the torque is anti-clockwise. Supposing if I turn this in clockwise, the torque will be in clockwise. Likewise, this torque experienced by the dipole is a restoring nature, and that is why I am using along with negative sign. Now you can say tau is equal to P sin theta is what is restoring torque, you can say, and that is why I am writing you here itself in the very beginning. I will write it as restoring torque on dipole. Restoring torque on dipole. So along with negative sign, let us use that, and tau is equal to minus P times theta. I call it equation 1. And one more definition of torque by using our concept or fundamentals of rotatory motion. Now I am writing by the principles of rotatory motion. Principles of rotatory motion. Yes, you remember torque, how did we define? Torque tau is equal to I times alpha was our definition. This I for moment of inertia, yes, the rotational inertia, times alpha, the angular acceleration. So tau is equal to I alpha. Now I call this equation 2. So now I will compare equations 1 and 2, right? So now comparing the equations 1 and 2, yes, you will see that as I alpha is minus P times theta. Small rearrangement and making use of one principle. Therefore now here alpha is equal to minus, yes, Pe by I. Negative of, yes, this expression please look at carefully, negative of minus Pe by I times theta. I call this expression some equation 3. Equation 3. Now we say it is making angular SHM, and for that let us use our understanding or our principle of SHM. Simple harmonic motion, what is the condition we write? If it is linear SHM, oscillations vertically or horizontally with the translational displacements, we write F is equal to Kx, K for force constant and X for that displacement term. Now but here it is not linear SHM but it is angular SHM. Therefore now I am using that principle of angular SHM, because translatory versus rotational is always easier, because in translational motion we call force, in the rotative motion the analogy is torque. Is it torque? In translatory motion if it is linear acceleration A, in rotative motion it will be rotational acceleration, angular acceleration alpha. So that is how we simply compare the things from translation and rotational. Therefore now again I am writing by the principles of angular SHM. By the principles of angular SHM. I have told you what do I mean by angular SHM. Remember, this is what is the dipole suspended, placed, you imagine, then oscillations are not like this, I have told you, but about its center it is making oscillations like this, the angular SHM. Yes. alpha is equal to omega squared theta, of course that negative sign because of restoring nature. Because in linear system, the expression for acceleration, you remember, A is equal to omega squared x with negative sign. A replaced by alpha, x replaced by theta, and this omega square is the same analog which we call it as angular frequency. So now alpha is equal to omega squared theta is the principle of angular restriction, we call it equation 4. Therefore now you will find that first we have compared equations 1 and 2, we got expression 3, and we have used the principle of angular restriction 4. Therefore now finally you got this comparing equations 3 and 4. Because you will see the same LHS, so now you will compare RHS, right? Alpha, theta term. Look at this expression, omega squared, and what is here? You will find this as minus PE by I. P for dipole moment, E for field intensity, and I for moment of inertia. Comparing, what is that you get? Yes, omega squared is equal to, right? Omega squared is equal to PE by capital I for moment of inertia, and from this you will write the expressions. And time period T, because we know omega is equal to 2 pi by T. Omega square means 4 pi square by T square, right? You write that, and I am writing the final answer. The time period, I will write, the time period capital T is equal to 2 pi times root of, yes, capital I by PE. This is the expression for time period. If you take it, the reciprocal, you will get the expression for frequency. F equal to 1 by 2 pi PE by I. Now, actually, I want to discuss about this result, time period, on which factors that it depend. But if I do that, because already the last couple of results that I have derived for you, I have shown how to look at a for expression, because you don't call it this as a formula as you call it in mathematics, because it carries a lot of information, knowledge, and that is what we call physics. LHS term versus RHS term, what are the constants and variables, how their dependence depend. And also I leave it to you only. If any one of you have that urge or hunger, you do that work, and also you can call your teacher. Supposing if I draw some graphs between time period versus field, time period versus dipole moment, all these things, time period versus moments of inertia, the dependencies, how to write ratios or how to draw the graphs, and what does those graphs actually mean, like they convey any such important factors, more factors regarding this expression. So all that will be your, I don't call it homework, that will be your due responsibility, right? So time period expression that I have given, and you write the frequency expressions, and of course afterwards whatever additional work you want to do, you please do and call your teacher. So this was about our topic of electric dipole in electric field. How do you look at this? For board examination, it is nothing but you have 3 to 4 questions and answers for 3 marks and 5 marks. To begin with, torque experienced by the dipole. Second one is, yes, the potential energy of dipole. Second question and answer, 3 marks, 5 marks. Third one is angular SHM of dipole and expression for time period, this which we have done. And all those expressions that you come across, you will remember them, you will practice them, and you can substitute and get answers. They become what are numericals for your board examinations, which most of the students feel difficulty in the month of December or January. So I am telling you, you follow this and do all these derivations twice or thrice. Wherever we have given those representations, wherever we have represented vectors, or wherever we have given stars and asked you to note it carefully, give a pause for the video and watch it carefully. Right? Eat well, sleep well, prepare well. Good day.